Miss Patterson here. Today we're going to go over physical and chemical properties. This is physical science. This is going to be a little bit of a longer video, so just be aware if you need to move forward, go ahead. So let's talk about physical properties. If I asked you to describe this tiger, how could you describe him? You could say it looks like a cat, has a tail, stripes, tan and white fur. You could say it has 2 ears, big claws. This is going to be to describe the tiger. If I was talking about a tree, I would not use these same characteristics. So this is going to be physical properties that would describe a tiger. If somebody gave you those characteristics, you would know what it was. And when we talk about elements, we kind of talk about the same things. They have physical properties too. They have characteristics that are just for that element, so I know what it is I'm talking about. So properties that can help to explain, one can be what's called viscosity. This is going to be the resistance of a liquid to flow. So if I look at water and I poured it down a board, let's say I had a board at a diagonal, and I pour water down that board, that water is going to move fast. So that means that it is going to have a low resistance. It's going to flow really, really quick. If I have something like pancake syrup and I put it on that board and I let it run down, it's going to run a lot slower. It has more viscosity. It has a higher resistance to a flow. If I did petroleum jelly like Vaseline and I put it on there, it would just stay. It's just going to barely slide down. I might come back the next day and it might be halfway down my board. So this petroleum jelly has a high viscosity. It's not going to want to flow. It's going to resist the flowing. But these are going to have different characteristics. If I want something that's going to move very fast, if I want something, for example, like self-levelers, they use a lot of water. Water is going to lay flat. If I want something that's going to be sticky, I need it to stay on stuff, I'm going to be looking at one of these two. So viscosity has some purpose. And we see that with oil. When we put oil in our car, we notice that we have different types of viscosity. We have W50 or 40 or 30, and that's the weight of the oil. If I am during the summertime, I want a high viscosity because it's going to get hot and my oil is going to thin out really fast. I don't want a super thin oil in the summertime. I need a little bit thicker because it's going to be hot. It's going to thin on its own. During the wintertime, I need a thinner oil. That oil is going to kind of come together. It's going to be a little bit more viscous, and so I need it to be, I don't want it to be real thick. This would be like jelly in my engine. So I need it a little bit thinner during the winter time. Different types of viscosities are essential. I can have high viscosity, and that's going to be paint. If I'm painting on a wall, I don't want it running down and puddling on the floor. I need it to stick to the wall. So paint has to have a high viscosity. Peanut butter is going to have a high viscosity. So certain types of foods are going to have that. You want pasta or spaghetti sauce to stick to pasta. You don't want it running off the pasta. So there's certain things that we want a high viscosity for. Low viscosity, we want that too. We just don't want everything to have a high viscosity. So low viscosity oil, if I'm trying to lubricate something, gears, I want some type of oil. And self-levelers, we talked about that a second ago. If I have cracks or my floor isn't even, and you'll see these with people who work on floors. If my floor is kind of dipped, they can put in, it's almost like a concrete, and they put a lot of water in it. So the water will go in there, fill all those nooks and crannies, and it will lay flat. If I took water and I poured it on the floor, it levels out, and it levels out really nice. And so it will go out that way. So they put it in a lot of levelers. So they'll take this, they'll push it, and then the water will kind of help this leveler kind of level out and be flat and fill any nooks and crannies, any holes in the concrete. Another physical property is conductivity. This is the ability of heat or energy to travel through a substance. So for example, if I took a metal rod and I put it in a flame like a candle, the heat is gradually going to go all the way through it to where eventually I'm going to be able to feel it with my hands. We notice this with a skillet. If I go home today and I want to make a grilled cheese sandwich, I put my skillet on the stove. As soon as I turn on the stove, the skillet's not hot instantaneously. It takes a little bit of time for it to heat up. Now let's say I leave it on my stove and I come back an hour later, that handle's going to be hot. All those molecules have passed that heat along and have moved it down that handle to where now it's there. It doesn't happen on its own, but it's conductive. It moves heat energy through it, and I want that. If I want to cook food on a skillet, I need it to be able to move heat energy from the skillet to my food, and from whatever I'm cooking on my stove into the skillet. So here I can see something like this. I can see when something is red. This is very hot. It's almost to the state where if I let it stay long enough, it can start to melt. But these are going to be the heating elements for a stove, and this is going to touch the metal skillet, and then this is going to transfer the heat energy from this into the skillet. And when this turns off, it doesn't cool off right away, right? It takes a little bit of time. So when things are conductive, it can take a lot of time to heat up. It can also take a lot of time to cool down, but there are some that will heat really, really quick. So let's say we're doing laundry day and your dryer just stops, you're sitting there waiting for it, you need a pair of pants, and you put your hands in there and something burns you. All right, what is it in the dryer that has burned you? It's going to be some type of metal, like a metal button, metal zipper, and that burns your hand just for a second. You throw it in the basket, you go back to your room, you dump out your clothes on the bed, and it's no longer hot. Okay, so now the question is, well, why? It just burned me just a second ago. I don't have a lot of matter in this button, and so this button is only holding a certain amount of heat energy. So this is going to cool off pretty quick. So when I take it right out of the oven, it's going to have that heat energy. It's going to be very conductive, but then as soon as I get from my dryer to my room, it's had enough time for that energy to be able to leave. Now let's say it's a hot summer day, middle of summer, and you're at a park, and you have the choice of two slides. So this slide right here and this slide right here. And which slide would you want to slide down if you're of sound mind? Okay, which one are you going to want to ride down? So this one's going to be a lot hotter. So this one's going to be metal. This is the one that's going to burn your legs as you go down. These are the ones we had as a kid. And so this one was not played with very much during the summertime. Now this one here, can it get hot? Yes. Is it going to be enough to really kind of burn you like this one can? No, but it's still going to get hot. But it's not going to be as conductive of heat as the plastic one. So another physical property is malleability. And basically it's the ability of matter to be hammered and contoured without shattering. I say this is the ability to beat the fire out of something and it not break. Okay, so remember those penny presses you see whenever you guys go on vacation or you go to like the zoo, and they have these penny presses in it. So what's happening is there is a mechanism inside where the penny goes in and then it heats it up real fast. It's a really hot plate and it pushes down on it, and then there's a image that you want pressed on it and it pushes into it. So it heats up the penny real quick, and it's enough to be able to heat it up enough where it can press an image into that penny. And so here you can see we collect a ton of these things. We got them from all over the place. And so these pennies here are ones that we've gotten, and these have been pressed. They're malleable into that coin, so you can have an image in there. And when it doesn't break it or anything. And when you get the penny out, it's warm, and it's from the heat that was inside that machine. Temperature can affect malleability. So if something gets really hot, okay, I can take a hammer, I can mold it, I can flex it. It's going to be more malleable the hotter it is. And something else that can be really fragile but very malleable when hot, it's going to be glass. So here I can take glass, it's super hot, and I can take it, I can bend it, I can do stuff with it, and it's not going to break. But as soon as it cools down, now it's going to be fragile. Now it's going to shatter and break. So temperature can affect malleability. Another physical property is going to be hardness. This is going to be the ability to scratch another object without damaging it. So there's what's called the Mohs hardness scale. And geologists do this when they go outside. They need to be able to identify what types of rocks they have. And they can do things like their fingernail, or they can take a penny, or they can take a nail. If they can scratch talc or gypsum, if they can scratch a rock with their nail, then it's going to be one of these two. If I try to scratch this with my nail and I can't, I know it's not talc or gypsum. If I can take a penny can scratch any of these. A penny will scratch calcite, but it can't scratch fluorite. So if I try to scratch a rock and it doesn't scratch, it's going to be fluorite, it could be any of these up here. Now, if I have a screw or a nail and I can scratch orthoclase or apatite, if I scratch that, then I know I'm going to have one of these. It's not going to scratch quartz or topaz. So they can do things real quick and kind of do a quick identifying of what they think it's going to be. So let's say you go to a jeweler and you have a ring and you think it's a real diamond and you want to double check. They're going to take it to the back and they're going to do a couple little quick tests on it. One of them could be a scratch test where they take a ruby and they scratch it. If a ruby scratches what they think's a diamond, it's not a diamond. A ruby cannot scratch a diamond. A diamond is the hardest material, natural material we have here on our planet. And so a ruby cannot scratch that. So if a ruby scratches this, then it's not a real diamond. Now a diamond can scratch a diamond, but a ruby cannot. So same thing, if I have a ruby, a red stone, I think it's a ruby, and a topaz can scratch it, it's not a ruby. A diamond can scratch it, but a topaz, quartz cannot. Okay. All right, another physical property is going to be the melting point. This is the temperature needed to change a substance from a solid to a liquid. So we have something like ice. Okay, I know that if I want ice to freeze, it's going to be at 32 degrees. If I want ice to melt, it's also 32 degrees. So 32 degrees is, if you've ever remember our latent phase change we did when we did states of matter, I have an energy level right there, and that's when energy is going to go from freezing to melting. I can jump back and forth during that time. So the melting point is also the freezing point. So this is going to be 0 degrees Celsius, or it can be 32 degrees Fahrenheit. All matter has a melting point, and so here we have lithium. Lithium is going to be here, silica is going to be here, and look at carbon. Carbon is way up here, and you look at carbon, that's going to be 6,332 degrees Fahrenheit. Okay, that's 3,500 degrees Celsius. That's very, very hot. Okay, so this is going to be the point when you're going to start seeing rocks and melt and magma and all. You got to get super hot to be able to start to break down and melt carbon. You have other ones. Here are some metals. So you can see here the melting point of certain types of elements. So the gases you see, they're already kind of at that point. This is 0 degrees Celsius, so 32 degrees Fahrenheit. Okay, it melts. It's already a gas at our room temperature. So this has a very low melting point. Another physical property of matter is your boiling point. This is the temperature needed to change a substance from a liquid to a gas. So here I have water. I put it on the stove. And remember our latent phase change. This is when I go from condensation to evaporation, or evaporation through condensation. That latent phase change, which is 100 degrees Celsius to 112 degrees Fahrenheit, this is when I go from one state to another. So if I took the temperature of this boiling water, it would never get above 100 degrees Celsius. That energy is being used to move it from a liquid to a gas. So density is the ratio of mass and volume to determine the purity of a substance. So I have to find the mass of an object and the volume of an object to do that. I have a density video on this too, if you guys need to see about density. So here I have different objects, and different matter will have different densities. And I can put them in a tube, and I can layer them just like so. So here I have honey at the bottom, which is really viscous. It's very heavy. I have maple syrup. I have milk, which is a little thick. It's a lot thinner than water. Dish soap. I have rubbing alcohol, vegetable oil. All of these are going to have a very specific density. I can put objects in it. So a soda cap, a bead, a cherry tomato, a die, which is 1 dice. I have popcorn kernels, a bolt. And if I put these in here, these also have very specific densities, and they will stay within this area. So this cherry tomato's density is less than milk, but more than water. So it's going to sink in water, but it's going to float in milk. So all of these will have a very specific density, and these can be a property that can identify a substance. So for example, you're told that an object is pure gold, and you think something was added to it. So I give you a crown, and I tell you it's 100% pure gold, and you're like, I don't know, Miss Patty, I don't know if that's going to be pure gold or not. So you want to double check. So you know that gold has a density of 19.3. It's the heaviest natural density object that we have on our planet. And I want to know. So I'm going to put this in water and I'm going to find the displacement. I'll find the volume of it. I'll take the mass of it, the volume and the mass, I divide that, and I get a density of 18.9. That is telling me that this is not pure gold. There is something else in here that has changed the density. If I had a pure gold bar that was as big as a bus, and a pure gold bar that was as big as a penny, okay, if I took the density of that, the mass and the volume, I will always get this number. It doesn't matter what size. Now, if there's something else in it, I will not get that. I can have different objects, different molecular formulas will have very specific boiling points, very specific densities, and it can also tell me what state they are at that temperature, at that type of matter. Forensics are going to use this a lot, so they're going to use these properties to be able to help identify a substance. So if you're given something in a crime scene and it's a fluid and you don't know what it is, you're not going to taste it, you're not going to smell it, you have no clue. So you have to be able to do tests on it. So you're going to see a density test, you're going to do a melting, a boiling test, you're going to do all of these physical properties to figure out what it is. Just like with the tiger. I said it had stripes and it looked like a cat, it had a tail. So if I'm giving you all this information, you're going to start coming up with a picture of a tiger. And if I start giving you information about a fluid, you're going to start to get a picture of what this fluid could be. Is it blood? Is it some type of hairspray? Is it gasoline? Is it, so it's, you're going to have very specific properties for each of these types of liquids. I can separate them so they can do a physical separation. I can filter them out, and when I filter, I'm going to have larger objects are going to be blocked through some type of mesh, some type of paper. Something's going to hold one part of the object back and allow another part of it to come through. So examples are tea. I can take a tea bag. Inside I have tea. The tea can, parts of the tea can seep through the bag and then it's going to get into the water. I can see this with air filters in cars. And you can see this one's dirty. It's going to drive through and then these pieces of paper are going to hold back the bigger dust particles, bigger pieces of debris that will get into your car and it will filter it out that way. You can also distill, which means you're going to separate it based on boiling points. So you put it in something and then you boil it and then you separate stuff out. So you can see this if you go to like the salt flats in Utah, or you go to the Dead Sea. You have a lot of water here and it's full of salt. And so the salt water is going to sit and then it's going to get hot and this water is going to evaporate out and it's going to leave the salt behind. And then it's going to look like this. I'm going to have all this salt crystal left behind, and so it's going to separate out based on its boiling point. My boiling point of water can be hot enough where it's able to evaporate out. You'll do this with, they do this with distilleries. If they're making like some type of beer or alcohol, they'll do that. If they're trying to separate something out, they'll boil it and get the lighter stuff on top and the heavier stuff on bottom. They also do this on submarines. Out in the ocean, they can't drink seawater, but they're just covered in water. They're in a big, huge ocean. And so they can take water from the ocean and they can turn it into clean water. So what they'll do is they bring water in and then they're going to heat it up and they're going to boil it. And as they boil it, all the heavier salts, all the junk that's inside the ocean is going to stay down here. The water steam, because now we're in a gas form, is going to come up. And as it comes up, it's going to cool. They're going to have cooling water up here. And then this cooling water is going to cause the steam to condense. It's going to go from a gas back to a liquid. And then as it does, it's going to come out and it's going to fill a reservoir. And this is going to be clean water. So submarines can use boiling points and they can distill water out of seawater. When you have a property of a substance change, but the substance at the molecular level stays the same. So when we think of physical changes, you need to think it's changed, but is it still the same thing? So we see this with water. I have water, which is H2O. I can have water in a solid form, which is ice. I can have water in a liquid form, okay, which we can drink. And then I can have water in steam, okay? But these are all still the exact same molecule. The only difference is how they're together. These are really packed tight. This is going to be closer together, and these are far apart. But my molecule itself is still the same. It has not changed. As long as my molecule stays the same, I'm fine. It's just like me taking a piece of paper. I take a piece of paper, I rip it in half. Is it still paper? Yeah. I'm not going to rip it in half and it turns into flowers. Okay, that just wouldn't make sense. It still has to be, this molecules are still there, nothing's changed. So examples of physical change. I could be squeezing an orange and making orange juice. I could be crushing a can. I could cut hair. I can mow grass. I'm changing the way it looks, but it's still the same thing. This is still orange juice. This does not turn into cranberry juice. I crushed a can. It doesn't turn into a shoe. I cut hair. It doesn't turn into bread. I cut grass. It doesn't turn into kittens. Okay, so all of these different things, they're still the same thing. It's just in a different type of look. So now let's talk about chemical change. So physical change, where it stays the same and they have certain properties. Chemical change, now we're changing the bonds. We're changing everything about what it is. So it's a change of a substance that reorganizes the atoms. So here I have CH4 and here I have O2. And when I put these together, I make carbon dioxide and I make water. So here you can see this was one molecule. Okay, I have these 4 white hydrogens and 1 black carbon. And here I have 2 oxygens and 2 oxygens. But now over here, look, the black one has 2 oxygens and these 2 oxygens now have 2 white ones on there. So this has totally rearranged, okay, the molecules. So now this is a chemical bond. I'm not going to be able to go from here to here. I've had a change. And usually it's going to be some type of heat, some type of pH. Something here is going to trigger it where it's going to break those bonds and allow them to rejoin in a different way. So baking a cake is a chemical change. I take all of these substances, I put them all together, and I stick them in the stove. And if I just stick it in the stove, nothing's going to happen. Because what do I need to do to be able to bake the cake? I need to be able to add heat. So when I add that heat is now rearranging, breaking the bonds of the flour, breaking the bonds of the sugar, and it's going to cause them all to come together in a very specific way. When I add that heat, I'm going to make the cake. I'm going to make carbon dioxide, is what's going to cause the cake to rise, and then I'm going to have that. I can't take this cake and I can't go back to this. I can't break this cake down back into the egg, back into the sugar, once that heat has been added. If I mix this up into a bowl, I could separate it all out. It would be hard to, but technically you could. But once I add that heat, I'm changing those bonds, and now I have something totally different. Can any of these objects go back to their original state? So let's look at these. I have a rotted apple. Can I get this apple to go back to its original state? No. So this is a chemical change. I look at an egg. I put an egg on a skillet and then I fry it. Can I get this egg to go back to its original state? The runny white yolk and all the stuff. No, once I've cooked it, I can't uncook a fried egg. Fireworks. Can I get these to go back? It'd be nice, wouldn't it, if I could put these back in a container and reshoot them off. And then a bike. Here I've got rusted bike. Okay, if I can't get this to go back to its original state. Rust just starts actually breaking down the iron, and things that can get rusty can start to fall apart because the molecules are being pulled apart. So another property is flammability. This is going to be flammable. The ability to burn in the presence of oxygen. So for me to burn a firewood or to have a campfire, I have to have oxygen present. So this is going to be the ability to be able to do that. So oxygen has to be there to be flammable. So when you guys were little, they would always say if you ever caught on fire, just stop, drop, and roll. So now my question is like, why does that work? So when you're rolling and you're pushing against the ground. And when you're pushing against the ground, you're pushing oxygen away from the flame, so you're starving it. So you're changing the property of something to be able to burn by removing that oxygen. Another one is reactivity. This can easily combine with other substances to create a new one. So you see all this rust? Okay, once a car starts to rust, you can never get that to come back. If you ever had to fix it, you have to cut out the bad part and you have to cut out part of the good stuff too, because this will just kind of keep breaking down and going through. So once something starts to fall apart, you can't get it to come back together. I can have changing colors. So here I can do a flame test in chemistry where I can take different elements, I can put them in a flame, and they will burn a very specific color. So that's a property of some of these elements, is that their chemical change will have a very specific color. I can have what's called a precipitate. Okay, I can have something fall out. That can also change colors. When your leaves change in the fall, these leaves are doing a chemical reaction. They are changing colors due to changes in the chloroplast and stuff. And once this leaf starts to change, you cannot unchange it. I can't get it to go back to its original state. Another one is a gas is produced. Some of you guys have done the little volcanoes with baking soda and vinegar, and it's going to produce a gas and it foams out all over the place. If it produces a gas, that's a sign that a chemical reaction could be happening where you're breaking those bonds and a gas gets produced. Another one is a precipitate. So here you can see I have a clear fluid, but when they come together, they make something different. So remember we talked about elements. Their elemental parts can be a lot different than the compound part. So this part here is one type, this is one type, but together I'm making something new. So this is going to be a chemical change, and a precipitate is a solid that falls out of a solution. So two pieces come together and I have a solid that comes out of my solution. All right, that's physical and chemical properties. Hope that helped. If you guys have any questions, let me know. We'll talk to you later.